All right. Thank you all for joining. Let me share my screen here. And all right. Hopefully you can all see that when it comes up. It's still thinking about it. That's in people's view, I hope. So
yes, we can see it.
Great. I'd like to start off by saying this is an interactive seminar. I've talked too many times just to the void of the camera on this screen. And so I would like to make it a back and forth today. So I will be having several slides where I have a question and either a chat window entry of your responses to it. And so please just start typing into the chat window and we'll watch many different answers appear there and scroll down. Or sometimes I have polls. And so Cheryl has worked to get those polls into the Google Meet system here for today. So hopefully all of that goes smoothly. With that, I will start off by asking you a question. When you think about metrics, so this talk of data model comparisons, we use the word metrics to describe that a lot. So what is the first word that comes to mind for you when I say the word metric? And yes, I really am going to sit here and wait for people to type. So,
a distance.
A distance, yes. Okay, I see measurement in the chat. Quantification, yes, that's a big thing. Just one measure. Yes, thank you, Astrid. We will come back to that. So, thank you. So for metrics in 2017, CCMC organized this conference, the Space Weather Capabilities Conference, and I led one of the focus groups, the working groups for that, on geomagnetic indices and the metrics that we use for those. And so from that, Masha Kuznetsova organized a special issue of Space Weather, and the working group there wrote a review article by committee, and we came up with this chart. And I'm occasionally going to look and point off to my side because I have the presentation open on a display over here. So if I occasionally look like I'm not talking to you, it's okay. I'm looking at what I'm trying to present. So on this, we had several big tables there in our review of how people use data model comparisons in their validation efforts of models that predict geomagnetic indices, in particular DST, KP, AE, AL, several others that we included in that review chunk of the paper. And this is one of those tables out of it, the smallest of them, because otherwise it wouldn't fit nicely on this page. And so the last column of this is metrics, and that were used in these particular papers here. And so what I'd like you to see is that there are actually a lot of different metrics on this. Can you see my cursor moving up and down maybe? Is there any hope of that? No?
Yes.
Yes, all right, good. So yeah, so here in the metrics, you can see that this person right here, R and RMSE. R is the Pearson linear correlation coefficient, RMSE, root mean square error. There are some others here with R, RMSE, MAE, and R, RMSE, and R, PE, okay. RMSE, R, POD, TSS, nice. Okay, so a few different ones. Quite a few people use lots of different metrics in that, and that's one thing that we noticed. So now I'd like to open a poll window for us How often do you include data model comparisons in your research? Cheryl, is this?
Okay, so I just launched this. Do you guys see a poll or anything?
No.
Anyone? Uh-oh.
Yes, it comes up as a, for me, it come up as a little box that you need to click on.
Do we click on the triangle stuff and then the polls?
I have no idea. I cannot see the box.
Yeah, at the top, there the triangle stuff, and then you can click on it.
Yeah, saw it.
Okay. How are we doing? I can't actually see that.
Yeah, so I can see when people add, I can see the different values and the different answers. So right now I've got 7 and 12. I have about 22 people have answered already.
Nice. Can anyone else see the answers, or are we all just seeing the chart itself?
I can see.
Can you see the answers?
You cannot, Wenbin?
I can.
Oh, you can. All right,
Yeah.
good. So I cannot see the answers in this presentation mode. It doesn't allow me to show that. Oh, maybe if I click on the little polls here on the side, maybe I can see it there. Polls. Oh, I can vote on one of the polls. So how are people doing here? If I click this and I vote, now I can see. Okay, so if you vote, then you can see the answers. So where you need to go is over into click on the chat, and you can see the left-hand column. Then you can, I'm sorry, the right-hand column of the meeting details, and then you click on the activities, which are the little triangle, square, circle, tiny button. And then you can click on polls, and then click on the one poll that's there. Once you answer it, you can see the answers. So a lot of people are saying usually you include some sort of data model comparison in your research. Okay, all right. So thank you very much for participating in that one. So now let me continue on. So the problem we face here is that there are a wide variety of metrics out there, and we seem to often go to RMSE and R as two common ones, and this isn't a bad thing. But it is a limited view. And so I'm just going to say right now, the point of this presentation is that I'd like for people to consider stepping back from that, from a narrow usage of data model comparisons, and really think about a bigger, broader view and choosing the metrics that are best suited for your particular needs of your of whatever assessment that you're conducting at that particular time. So let me go on to our next one. It's another question, another poll. How often have you used R and RMSE as the only data model comparison in a study? There should be another one coming up.
So you should find it in the same place, up by activities, was it?
Yes, if you had the polls open, then it should just appear right there as another poll in your set. And this is the one that's live right now. So options are never, because I don't do comparisons, never, because I'm a robust comparisonist, or varying degrees of using only R and RMSE in your comparison. And apparently I have to answer two, otherwise I cannot see the results. So there, the results are coming in. People are answering. All right. A few more votes coming in. I'll give people another few seconds to click on a response. All right, so hopefully you're looking at those answers now, and I see that we have a couple that don't do comparisons. We do have some robust comparisonists in the audience today. That is fantastic. A lot of people are in the are in the sometimes category though. So this is something that we do occasionally, is just to pick a limited number of metrics. It's often that the data model comparison is, you just want to say, oh, the model is good for this, and now let me use the model to explore some other physics. It's getting pretty close to the data, and so you just do one or two metric comparisons, data model comparisons with one or two formulas in the range of possibilities. But there's a really big range of possibilities of different metrics. So what happened to my mouse? Okay, my mouse isn't working anymore. There we go. So the large zoo of metrics that are out there, lots of different options here, and it can be confusing to know which one of these that you should be picking from. Oftentimes we're just picking out of this some, well, that one looks good today. I haven't used that one in a while, I'll pick that. Yeah, that can be one approach to this method of doing data model comparisons. This, I'd like to go straight to the punchline of the talk. And so if you can just take a snapshot of this and call it good for the day if you want. So this is, I'm going to spend some time going over what this is, but this is trying to organize that big confused splash of many equations on the previous slide into a nice organized system of how to use metrics. And this allows you to then better choose which metrics go best together with each other. If you know what type of categories you have that are assessing different features of the data model comparison, and even what type of groupings you have, there are actually two big methodologies of how we go about doing data model comparisons that are common in our field. And those two I call fit performance and event detection. And metrics can fall within one of those two in terms of how you go about even calculating the metric that you're getting to. So knowing this big collection allows you to better get at probing some specific aspects, because each of these categories are only really addressing one category. One specific little facet of the data model comparison. So what's your favorite metric? Now I have to get out of polls over here and get back over to chat box. So please go to the chat box. You just saw that big list here. I'll even go back over here and go back to this, so at least you have the acronyms in front of you. What's your favorite metric out of all of this? If you could pick one off of this list, please use the chat box. Good answer, Barbara. Yes, that's true. It's hard to pick one. RMSE is definitely a common one. That's true. RMSE is famous. We should. Other people have ME. Ooh, okay. Yeah. Nice. Thank you, Josh. All right. Any other thoughts on favorite metrics? All right. So let me continue on. So first of all, I mentioned that there were all these categories as well as a couple of groupings. So first, let me talk about those two different groupings: fit performance and event detection. Fit performance is really where you're taking the individual values of the model value and the data value that are paired together and comparing those two exact values against each other. Usually it involves a difference and then some operators of squaring or summing and sometimes with logs and other things thrown in there, but it's using all of those data model pairs and the exact values of those data model pairs together. Another one, that's one set. That's where RMSE lives, for instance. The other set is the event detection metrics. And that's where you specify a threshold for event identification in the data and the model. Sometimes those are separate because sometimes the model is actually a driver that doesn't even have to be related to the specific units of the data in this case. But when you specify those event identification thresholds in the two, then you can classify all the model values as event state or not event state, and all the data as event state or not event state. And this allows you to create something called a contingency table of yes/no values. And then from that, you simply add up the number of points in each of the quadrants. And the metrics are all based on those counts. No longer do you care about the specific value of MI or OI. So here's a picture showing the same set of data. And if you in the fit performance, you actually care about what is the level on the O axis, what is the level on the X axis, on the M axis, and you're doing some comparison of how close it is to the one-to-one diagonal line or some other assessment that way. Specifically with all of these MI-OI pairs. In event detection, you draw these two lines. They don't have to cross at the purple line. They can if you set the same values, but they don't have to. And then you just count the number of points in these quadrants, and you name the quadrants. Hits, yay, that's a good value to have. Correct negatives, yay, that's another good value to have. That's where you want all the points, but you might have points in the two error bins, the false alarms or the misses when one or the other are in event state and the other is not. So, but you don't actually care whether this point is way up here, far from the red line, or whether it's way down here close to the red line. Both of those count equally as a miss. Whereas over here, those two same points would count quite differently when you're doing the calculation of something fit performance metrics. So that gets us to these different categories of metrics, because there are metrics from each of these two groupings in all the different categories. So I'm just going to go really briefly through these different categories just to give you a flavor for why you even have such different things. So the big one is accuracy. And so why is RMSE such a famous one? It resides here. It's an overall assessment. It gives you one number that distills the entire data model comparison down. How close did the model come to the observations? And that's good. It's often considered the most important, and because it's doing this overall assessment. And if you get that close, you really are done with it. If this one is close, if this one is near zero, all the other metrics should also be very good, but they don't have to be. And by the way, there are many metrics that fit into accuracy. RMSE is one. Mean absolute error is another one that people like to use. That's without this square right here. Instead, you put in absolute values around this, and then this one right here, the median symmetric accuracy, is one that I really like for space physics, especially when things are highly dynamic and changing over orders of magnitude, because this one isn't susceptible to the outliers of the difference here. This one is taking a median of that difference, and it's using logs so that it treats all decades equally. So I like this one when I'm comparing things of fluxes, for instance. Say I saw Howard Singer on here, so I'll pick on GOES magid values, for instance. And do you want to do RMSE? It's going to be dominated by those in the upper order of magnitude. Only those times where you had really large fluxes, those will dominate the RMSE calculation. If you do MSA, then it's based on it takes into account those lower decades of the full range of the data in that calculation. In event detection, I like CSI, the Critical Success Index. That's one that puts hits over hits, false alarms, and misses as just a proportion correct is its own thing. That includes correct negatives in the numerator and denominator. But it's just like that. But we often have in space physics a lot of when we're dealing with events, our events are rare, and so I like to use CSI because it takes out that bias of having so many correct negatives usually in our models, in our data model comparisons, just because there are so many, there are so few events. So this takes out that and really focuses on actually, are you getting events? Another one is bias. This is thank you, Josh, for mentioning ME. ME is in bias. This is really looking at the discrepancy between the two number sets, and really you're looking at, are the centroids of the two number sets the same? And so the model, this is often characterized by the arithmetic average, the arithmetic mean, but it doesn't have to be. It could be geometric mean or median or some other value that you're comparing. But comparing two centroids and just are the two data sets shifted from each other, that could be part of why the accuracy is bad, is because you have a bad mean error. And this can help to explain what's going on in RMSE, for instance. SSPB is the sign symmetric percent bias. And that is very similar to MSA. It complements MSA very well, but it has a few extra terms in here that it puts parentheses and absolute values in different places compared to what you had in MSA, and so that you get this one really compares the two centroids and whether they're different, the two median value centroids. There's a similar one, another value over here in event detection metrics, which compares the times the model was in the state with the times that the data was in the state. That's what you're getting at with the two, with frequency bias, which is FB over here in the corner. Precision. This is the third of this set. So what is precision? Precision, you think, okay, you're accurate but not precise. I have a slightly different definition there. Precision here, I'm using it in terms of the spread of the values. So where bias was a shift of the two values relative to each other, precision is the amount of spread of whether one data set is tight and the other is also tight, but they might be shifted. So they had bias, but they had very similar precision because they have the same spread. And so precision is we often use yield, which to me is not a particularly good choice. Yield is just comparing the maximum and the minimum, the full range of a model to the full range of the data. And that is a measure of the spread, the full range, but that's susceptible to outliers. And so I prefer this measure of precision, which is a ratio of the standard deviations of the two data sets. There is a metric actually called precision in event detection metrics, and this is hits over hits plus false alarms. So it's taking the times that model is in the state and saying how often do you get it. A similar precision can be developed for times that data are in the state, and that's hits over hits plus misses. So these two right here are measures of how often, when you're in one of the two states, you're getting the other one also in the state. That's a measure of how close that clustering comes to each other. Association. All right, so this is changing gears a little bit. Association actually doesn't have to do with how close the two number sets are to each other. This has to do with how close the trends between the two data sets are to each other. You can actually be really far apart and have a good association score. And why is that? Because this is measuring whether you're getting the up and down nature together. And it could be that your values are actually systematically off by quite a bit. But if there's a straight line relationship between the two, then the up-down motion of the X values should match the up-down motion of the Y values, the model versus the observation in this case. And so you might actually have a really poor RMSE score, but R could be very high because they fall along a straight line. It's just not a unity slope straight line. And so that's the most famous of the association scores is the Pearson linear correlation coefficient here on the screen. There's also a similar one for event detection metrics, and that's called the odds ratio skill score, given by this formula here. Extremes. Okay, so this is a metric category that also, sort of like precision, doesn't get used a lot, unfortunately, I think, because this one really is good for space physics because it focuses on those events that are the outliers of our data sets. And so really it's asking how close is that model to those outliers. And so here are two different formulas for calculating it. One of them on one side is kurtosis discrepancy. So calculate the kurtosis, which is this value. It's kind of like RMSE, but well, it's not. It's kind of like standard deviation because you're comparing the values against its own average, but you're taking it to the fourth power. And so that really exaggerates the influence of the outliers. And then you normalize it by the fourth power of the standard deviation so that it has some value there that you can say that, against a Gaussian, K should be 3. And then you can compare that for the model value and the observed value and say, are you getting the tails of the distribution correct? Is what this really says. And so if you are, then you get that. Then you get that spread. In event detection, if you really have rare events, but you only care about actually getting the event, not the values of it, then I like this one. The symmetric extreme dependency score is a really good metric for it. And what does this do? This one is really nice because it emphasizes the hits using these natural log functions in a way that it becomes very sensitive when hits are very rare. The more hits you have, actually, the less sensitive that SEDS becomes. And so this is only good actually when you have a rare set of hits or set of events in your two categories, so that this will if you don't have a high score, if you have too many hit events that are possible in the data in the model, then SED scores actually are difficult to get really high scores because of this denominator value right here. So extremes reminds, and space physics, I have to be reminded of, sending people to space. We've had some successful launches of sending people back into space from America. That's great. Recently, we just sent Bob and Doug to the space station, for instance. We've also sent Matt Damon into space several times. And I like the movie The Martian. I think it's a really nice book, too. If you wanted to read that, they go into more detail of how he survived. To me, I think they got the physics of it close, except for the rocket would never fall over in the Mars winds. So the whole premise of leaving him behind is a little silly. But okay, so we had to go get him in The Martian. I have another poll for you. In what other movie did we leave Matt Damon in space, and did we have to save Matt Damon from space? So we should have another poll open, and let me go over and click on the poll. You also should have poll 3 should be live, and so your 4 choices are Thor Ragnarok, Saving Private Ryan, Interstellar, and Ocean's 14. So, people are voting. Please vote. And we'll wait a little bit more for a few more votes to come in. Maybe I'm giving you too much time and you're able to go in and surf the web really fast and find which movies Matt Damon was in. Or not. Hopefully, well, okay, here we go. What is the correct answer here? I see that lots of people voted for Interstellar. A couple voted for Saving Private Ryan. Thor Ragnarok got a couple. Ocean's 14 got 0 votes. So let's, Interstellar is probably the most correct answer here. Matthew McConaughey is, sent off into space. They find this outpost where they had sent somebody before. They open the body bag and out pops Matt Damon, restored from deep freeze. Awesome. Okay, so yes, definitely he was saved from outer space there, but he was actually saved from outer space in Thor Ragnarok too. So that one is also correct. Anyone remember where he was in Thor Ragnarok? He was the guy that played Loki on stage. That Loki was in disguise as Odin, and there was a play going on stage right near the beginning of the movie. Matt Damon was actually on stage in costume as Loki. So that means that he was an Asgardian. And at the end of the movie, Asgard gets destroyed, and they had to save all the Asgardians and get them onto the ship and get them out of there. So I'm pretty sure that we saved Matt Damon from space in Thor Ragnarok. Saving Private Ryan, we saved Matt Damon, definitely, but not from outer space. We saved him from battle space of northern France after D-Day. And Ocean's 14 doesn't exist, but I'm sure if they made Ocean's 14, well, in Ocean's 8, did anyone see Ocean's 8? Ocean's 8 was a great movie, bunch of badass women. And Ocean's 8, they have scenes in there where they're at Danny Ocean's tomb. And so he dies at some point. And so I'm pretty sure that in Ocean's 14, which is yet to be made, it's an outer space thing where they're trying to do a heist on the International Space Station, and Matt Damon gets himself in trouble, and Danny Ocean has to save him and somehow ends up dying in the process. And so we tried to save Matt Damon from space in Ocean's 14 too. So really all of these answers are correct. Okay, let's go back over to this. And all right, so subsetting categories. There are some of these that, when you don't want to use the whole set of data model points in your calculation. And so for fit performance, this just means dividing up your range of either the model values or the data values and using just a subset of the points within a slice, a horizontal or vertical slice of your full data model set. And this is very useful, actually, because then you can apply the same metrics that you were just using on that slice and see what is the accuracy, what is the bias, what is the precision within that particular slice as a function of data. So in a specific range of data, that's called discrimination. In a specific range of the model values, that's called reliability. And this allows you to really probe why RMSE gave you the score that it did, because then you can do RMSE as a function of each of these different breakdowns, both as a function of subsets of the data and subsets of the model, and that allows you to explore why RMSE is the value that it is. In event detection metrics, the natural breakdown is above or below event state, and so there are various calculations. The two most famous there are are probably probability of detection and probability of false detection, the discrimination values of data in the state or data not in the state. Those two ratios, and we'll come back to those in just a second. So that's subsetting, and then a final category that I like to break things down into is skill, where you can use basically any of the other metrics that we've talked about in any of these other categories, and put them against a reference model value. And it usually takes the form of a skill score, the formula here on the screen. And various people have plugged in different reference models and plugged in different metrics and come up with some really nice skill scores that are commonly used in the field. And probably the most famous skill score is prediction efficiency. It's where you used the mean square error for the as the metric, and then which is the square of RMSE, and then used the observations variance as the reference model, and that gives you this formula over here on the left. Two in event detection that people love to use, Heidke skill score. It's probably the most famous of the event detection skill scores, and the other one is the Pierce skill score, also called the true skill statistic, TSS, which is often used. So those two get a lot of traction. They have the same, almost the same numerator of the two good quadrants minus the two bad quadrants. So both of these like to highlight a symmetry of hits and misses. I'm sorry, of hits and correct negatives. These scores maximize when these are when hits times correct negatives are actually about equal. It's harder to get a good score when you have rare hits in both of these skill scores. You can still get a perfect score if you have no false alarms or misses. If this is 0, you're going to get a 1 on the score. But so speaking of skill, I'd like to just bring up another sci-fi thing, and that is that, did you know that there are superheroes, very skillful people out there that come from space weather? The Fantastic Four is actually created by a giant cosmic radiation exposure. And so, yes, I have another poll for you here, just to keep things going. Which one of these three? There have been several different restarts trying to get the Fantastic Four going. And so which one of these various Fantastic Four incarnations is the best? So Cheryl, could you have the next poll open? And let me go to that. All right, people can vote on which of these. Yes, I put it up there because some people really don't care about being a fan of the Fantastic Four. That allows you to vote in this option. So here we are getting votes. I'll let that go for a little bit. Maybe 5 more seconds if you want to have a say in this. Okay, we'll close the poll because we left it at a time with even voting between the original comic book and the group from the 2005 movie. But it's pretty close. People, and really it's mixed feelings about the Fantastic Four. Quite a few people did not want to express an opinion about that. Okay, so back over to the presentation. One thing that is special about the event detection metrics, and that is that you have to define what these boundaries are for what is an event. And those values that you're choosing, those two thresholds, do not have to be any particular number. They can be something physically meaningful, minus 50 DST, for instance. That's somebody's definition of what a storm should be. But really, who picked minus 50? Why don't we slide that value back and forth? And so people have done this. And you can create curves for the metrics as you slide those event identification thresholds back and forth. And you can slide the value in not only what is the model setting, but also what is the data setting for an event. And this is especially useful, I think, if you're doing a model that is exactly reproducing values in the data, so that the two are trying to be on that one-to-one perfect line. You want the scatter plot to be a diagonal line of points. Then one way to assess that diagonality of it, but with event detection, is to slide both of them together. And so there are two curves that have names where sliding metrics or sliding thresholds happen. One is called the ROC curve, the other is a STONE curve. The ROC curve, I'm putting down relative operating characteristic here. There are actually a couple different names. The STONE curve is where you're sliding both of the event detection thresholds at the same time, and it has that name. So the two are very closely related, but slightly different. But ROC, people have strong opinions about this acronym. So I'd like to get your opinion. What do you think ROC should stand for? We have yet another poll going on in the box. So receiver operator characteristic was the original name, and then it started to morph into receiver operating characteristic and then relative operating characteristic. And some people say characteristic, why are you even using that? Drop it and put in curve. And so there's a couple versions using curve there as well. And if you, again, I left you with the option of not answering at all. So, so let me vote so I can see the answers, and votes are coming in. So please chime in on this. I'll give you maybe 10 more seconds. All right, so wow, awesome. People don't like the original name. I don't either. So so thank you for validating that thought. Okay, so yeah, whatever you can just call it the ROC curve. How do we go about working with it? You know, so the calculation of these is done in this way. So for the ROC curve, you set what the data event threshold is, and then you sweep the model threshold. And that keeps all the points in either above the red line or below the red line on this curve. And POD, producing these, you're going to plot probability of detection against probability of false detection, which are the two discrimination metrics from subsetting for event detection. And so that means that you're going to have POD is only above the red line, POFD is only below the red line. So therefore, these numbers will change monotonically as you sweep the blue curve from left to right. In the STONE curve, you sweep both of these together. This one can only be used when the model is trying to exactly reproduce the data. But if that is the case, then you can do this sweep of both lines together, still plotting POD versus POFD against each other. But now some of the data points, they'll all start out in hits and they'll all end up in correct negatives, but they can take different paths getting down there. And so what that means is that you can actually end up with non-monotonicities in a STONE curve. And so, so here's a comparison that I had in a paper last year that shows a ROC curve as well as a STONE curve for the same data set. It was done for this CCMC runs of the SWMF getting DST, compared it against real-time DST. and you end up with this curve, and you can see that the STONE curve has this non-monotonicity. It jumps up right there. And when you have these non-monotonicities, that tells you something about the data model relationship. And so if you are trying to exactly predict a data set with a model output, then a STONE curve is actually a pretty useful thing to do, because when you get these types of features like this non-monotonicity, this tells you, because what is happening? Probability of detection is going up. That means that you had an extra, that means that you have more hits than, because what is probability of detection? It is the hits over hits plus misses. And so what you have when this goes up, you have a bunch of misses leaving the miss category, going down to correct negatives. So in this case, you had an underestimate of the model. So you got of the model values trying to get the observations. So you had a bunch of points up in the misses. Your model value was too low compared to the data, and therefore you had a cluster of misses that now when you sweep the line past it, the red line past it, you end up moving those to correct negatives, and you end up increasing POD. And so this shows you that you were underestimating values in the 20 to 50 range, minus 20 to minus 50 range, and that's what happened here. So that's a useful little trait that you can extract out, and you get the same thing. You can also get wiggles back and forth in XY space. Each of those means something. So a quick recap: we have all these different categories of metrics, many different metrics within those categories. We have 2 different types, groupings of how you go about creating these. These things are, I've mentioned that, there are I have some favorites in each of these, and I've hinted at how to combine these, but really let's go about combining them. They actually work really well together. So I mentioned the trifecta of accuracy, bias, and precision. Accuracy gives you an overall number, but you don't know why it gave you a bad number. Let's say you got 15. When you do 2 other values, a bias value and a precision value, then the bias can tell you, if the bias is 12 and the precision is 2 on the same unit scales, okay, then I know. They don't necessarily have to add up to each other, because you might choose different things that have different calculational schemes. But that relative difference there tells you that most of the RMSE difference was due to bias rather than due to spread. And so that's one way to do it, to understand more about what's going on with your data model comparison. Another complementary pairing is accuracy and association. Accuracy tells you how close the points are to each other, the values are to each other, but association can tell you, is there this linear shift? It is, instead of falling on the 1-to-1 line, maybe you're falling on the half-to-1 line, and things are systematically, underestimated or overestimated, but in a linearly scaling way. Bias won't necessarily capture that, and neither will spread, but association will capture that linearity relationship between the two. So are you getting the up and down motion, even if your up-down is of different magnitudes? So those two go really well together. And then I really like the augmented experience of subsetting or sliding the threshold in the two different types of going about it. And I think that this is a great way to probe different aspects, specifically, in different regions, to really say, why did I get, a bad RMSE? Because then the next thing to do would be to slide those scales and see, was it sort of off only in the low region, or off in only the high region? This will zoom in on that and really tell you where you're getting things correct and where you need to improve your model. So as a final question here, what is your favorite pairing of 2 or more metrics? And I'd like you to go into the chat box for this. Oh, I need to go back to the chat box in order to see. Yeah, so pairing different ones. Yes, bias and spread are a really good pair together. I think that those two add a lot to the accuracy. It really breaks down accuracy into two things that are more specific. And remember, these, bias doesn't tell you about the spread at all, actually. So you need the two together. Those two work really well together. So I'd like for you to go away thinking about that, and I will just finish again with where I started with this summary chart. This is in a paper that's been submitted to JSDP, and it's in second round revision. I hope that it was a minor revision, so I'm hoping that it's accepted very soon, and that you'll be able to see this in print, or in press, I should say, at the website for that journal very soon. A final slide, I would like to acknowledge those that I've been working with on this, and various support for this. So thank you very much. I hand it back to you, Nick.
Thank you, Mike. That was quite interesting talk. Does anyone have any questions? You can either unmute and ask or type into the chat.
Hi, Mike. I'm wondering if you had anything to say about sort of multivariable metrics and or looking at vector quantities.
Yeah. No, I guess I didn't prepare anything about that in this. So no, I don't have anything off the top of my head to say about that, but I think it's really useful to for me at least. I like to break it down into two at a time and evaluate each of those pairings differently. I would be interested to hear about you. Yeah.
Well, and I think the only thing I would say to it, without going into any details, is that many of these metrics that you presented today do have sort of a multivariable version.
Yeah, good point.
And I think it's sometimes it's useful if you want to look at the overall quality of fit of a model or whatever. But sometimes it does probably confuse the issue.
Right.
So, Mike,
And I guess one thing I didn't mention was probabilistic calculations, where you run your model many times and you develop a probability distribution of the model output to compare against observations. That's a whole nother set of data model comparison techniques that can be applied as well.
So, Mike, this is Howard Singer. Thanks for an interesting talk and a useful talk. And this is more of a comment than a question. But one thing we didn't really get into is why we use these metrics and how important they are. And we use them certainly for guiding our science, next steps, based on whatever results we're seeing. But they're also terribly important for policymakers to decide, to make decisions based on the results that one gets from looking at data model comparisons with these various metrics. We certainly did that, for example, in space weather, like with the geospace model, and establishing metrics by which we were able to evaluate which models go into operations.
Yep.
Michael, this is Katie. I put a question into the chat box, but I'd like to expand. As one of the things we're looking at is looking at multi-population, not just multivariable, but multi-population evaluations. Do you know about, or point me to research and sources on, have people looked into how to do different metrics for this, that situation? In particular, things about like how to construct reference forecasts and that sort of thing.
Yeah, that's
good lead on that.
Again, not off the top of my head, but yeah, that's an excellent question because we really do deal with many different both input and output at the same time. Is that really what you're getting to, Katie? Yeah.
Yeah, sort of instead of sort of DST, I'll say, crossing a particular threshold, it would be between this and this threshold or between this and this threshold. So you can imagine trying to evaluate sort of small, medium, and large.
Yeah, definitely. All of the event detection metrics can definitely go into not just a binary contingency table, but a multi-level contingency table. That is definitely true. And all of those metrics, like Josh was saying, there are many different versions of these metrics. I've only shown you the binary version of all of these. Yes, there is a whole nother scale up of doing those as with discrete levels, bands, essentially, multiple thresholds. Yes.
Okay.
Mm-hmm.
Are you going to be addressing that in your paper? Is that addressed in your paper?
Only briefly in the discussion section. I did not include this chart here is the end of it, but we mentioned that. Yeah. Only a little bit at the end in the discussion. Mm-hmm. Mm. Well, I'd like to say thank you all for coming, and I guess I'm also like maybe we should all be watching the news now. Events are happening, actually. So.
Yes, if there's no more questions, thank you again, Mike. I think everyone enjoyed this and found it very useful.
Mm-hmm. All right, thanks.